everyone, in this video I'm going to be talking about the slope of our straight line or our linear diagrams. So when we have drawings like this is a linear diagram and we can draw these sorts of diagrams from linear equations. Now this is just part one. I'm going to address linear equations and their diagrams over a few videos. I did try to put it all into one video, but there was just too much content. And actually concentrating on just the slope for this video is going to serve us pretty well as an introduction because it is such an important topic. Now in general, our slope is going to tell us about how our vertical axis variable changes as we increase our horizontal axis variable by 1. So for instance, if I had this line here and you told me that the slope is equal to 1/2, that tells me that as I move along the line, so as I increase x by 1, our y measurement will increase by 1/2. And I can actually see that here. For instance, if we go from x is equal to 2 to x is equal to 3, that's a change in our horizontal axis variable by 1. Well, y is going to increase from here, I hope you could read that, that's 1.5 to 2. So y increased by 1/2, that's the value of the slope as the result of x increasing by 1. If I had a downward sloping line, then I would have a negative slope. So for here, for instance, if the slope was equal to -2, that just means that as I'm increasing x by 1, then my y value will fall by 2. And I can see that here as x increases from 1 to 2, y decreases from 4 to 2. So that's a decrease of 2. And just as I've been saying all along over the last few videos, x and y can be any variables that we're interested in. And once we realize this and we give our axes some more interesting labels, we can see just how important the concept of the slope is. For instance, on this axis, we're plotting total cost as we increase quantity. Now, the slope of that total cost function then is going to tell us about how total cost changes. So total cost is the variable on the vertical axis. So how that changes given a 1 unit increase in quantity, so in production. So it follows from this that the slope is going to tell us about how much it costs to make one more additional unit. And this is actually a concept called marginal cost. It's very important theoretically in economics. And so just to give a hypothetical application, if the slope was 5, then this means total costs increase by 5 if we increase production by 1. That is to say the cost of producing one more unit or the marginal cost of an additional unit is equal to 5. To give another example, if on our axes we had wages and years of education, for instance, then our slope would tell us about how our wage changes as education increases by 1 year. Again, a really important measure. We sometimes would refer to this as the returns to education. And this is a sort of relationship that economists might try to estimate if that's their field. Just to give you an application again, if the slope was 2, then this would mean that my wage would increase by 2 if I increase my years of education by 1. So the slope is a really, really important measure. And when we have linear functions, because they're straight lines, by definition, the slope is constant. Now we can talk about the slope of curved functions. I'll just draw one down here. So you can see in these functions, the slope changes as our horizontal axis variable changes. So I'll talk about these cases later on in the course when we do derivatives. So we do need calculus to deal with the slope of our curved lines equations. So you can look forward to that if you're watching that part of the course. Now there are a few ways to find the slope of a straight line, and I think the most common way is to take what we call rise over run. And so what we're going to do is we're going to look at our line and take any 2 points along our straight line. We will rise and run between those points, so take vertical and horizontal movements, and those measures will be our rise over run. So if we had this line here, for instance, we take 2 points, maybe where x is equal to 3 and where x is equal to 5. And I'm going to travel between these 2 points. Well, I could run forward, so that's a positive 2 run value, that's our change in our x value from 3 to 5. And I can rise 1 from 2 to 3, that's on our y-axis. So rise over run then will be, well, rise is 1 and run is 2. So the slope of this function is 1/2. You can do the rise first and then the run. It doesn't matter, the ratio will come out the same either way. If we have a downward sloping line, then we will either run backwards or fall at some point, and that will introduce a negative in the ratio. For instance, here between maybe these 2 points, I can run 3 And the grid here is measured in halves. So I hope that you can see that I'm running from where x is equal to 1 until where x is equal to 4. And I fall 1. So the y value is going from 3 to 2. So that's a negative 1. So my rise is negative 1 and my run is a positive 3. So our slope is negative a third. Now with our rise over run, we might see this written as change in y, or the change in the vertical axis variable, whatever it is, over the change in x, the change in the horizontal axis variable. So this is another way that you might see our slope written out with these triangles here, which means change. And actually this fraction, if you think about it, leads us right back to our definition of the slope, since this fraction can be read as the change in y given a change in x, or another way to see that fraction is that we're normalizing the change of y to be in terms of a 1 unit change in x. We're dividing out that change in x. Now, before I finish the video, I wanted to go through a few observations that follow from these discussions. So it does follow from this that the larger the slope is in magnitude, the steeper the line. So I'll put some drawings down here. So here is a slope of positive 5, positive 1, and positive a third. So you can see as the slope gets smaller, we get a flatter line. And actually, if we have a perfectly flat line, we're going to say the slope is equal to 0. Now, this works with negative slopes as well. So here is a slope of negative 5. It's pretty steep in comparison to negative 1 and negative a third. So our line is getting flatter as the slope is getting smaller in magnitude, or we might say in absolute value. Now, if we have a perfectly vertical line, we would say that the slope is undefined. Remember, the slope is equal to rise over run, so changing y over changing x. But if we only have a vertical line, then x isn't changing, so the change in x is 0, and we can't divide by 0, so it comes out as undefined. All right, that's it for this video. In the next video, I'm going to discuss a very common way to write out the equation of a straight line called the slope-intercept form of the equation of a straight line. As always, thank you so much for watching my content. I hope that it helped. If you would like written notes to help you on your journey, or even just to support this channel to help me make more videos, you can visit my store. There's a Shopify banner below this video. The notes associated with this video and this course include lots of practice questions with solutions, which can really help you solidify your understanding of the skills discussed in these videos. If these videos have helped, please like and subscribe, comment below, share, all of that. It all helps. Any feedback also is really welcome. Thank you so much for watching my stuff again. Have a great day, everyone.